Move on down the front. There's plenty of room. Move on down.
No, still ain't got everything. When I got the audio.
Okay. We're just waiting for the last few people to join, and then we'll. No, this. There we go. There's still more coming in. They're still coming in.
Mad fools.
I
remember to press the record button at the beginning this time, which is always
yeah, that's
a good start.
Yeah. Righto. I think. We've got Steve Richards has just come in. Jack has just come in. Move on down. Plenty of room at the front. Bring your ice creams with you.
And your beer.
Indeed, indeed. Oh, I've managed to move the slide on. That's always good. Right. Okay. So I think we'll make an official start then. So welcome everyone. Believe it or not, we're at week 4 of Stargazine. It seems to have gone rather quickly. Great to see you all here. And again, we hope we've had a good week, I should say. It's been lovely weather here in Bedfordshire. I've been busy laying patio slabs. I'm knackered, I tell you. So I'm Daz. I'm one of the admins here at Stargazers Lounge, and my co-host is Grant. What background are we on, Grant? We've got the Horsehead.
Horsehead and Small Child.
Horsehead and Small Child, yes, yes. So Grant's going to make sure all the technical stuff works. And as a reminder, as you might have heard, that we are again going to be recording the session, and we'll post that up a bit later. You will see a little red recording icon on your screen somewhere just to remind you. And again, as per the other sessions, we'll keep you on mute just so that there is no noisy distractions. It's great to see the ongoing discussions that these sessions are generating, and we are really hoping that we're going to be able to start some midweek sessions as well. Probably some smaller topics, perhaps 2 or 3 people, and we're hoping to kick this off on Wednesday the 17th. So in that's 3 days' time, isn't it? 2 of the mod team, Mark at Beaufort and Lunator. Mark's going to do some talk around visual observing, arrangements and processes and procedures that he goes through as he sets up for his observing sessions. And Ian's going to be talking about his most favourite subject, which is double stars. So hopefully we'll see you in those sessions. And of course, we're hoping to arrange more of those as we go on. We're just waiting for the final confirmations that Mark and Ian are available, and then we'll confirm that obviously on the forum. Again, as per usual, if you've got some questions, please use the chat facility. Grant and I are monitoring those, and we'll pick those up at the Q&A session at the end. And again, we love your feedback. Please head over to the appropriate boards on the forum and join in the discussion. Okay, so let's tell you about Steve Tonkin, our speaker for this evening. Steve is usually found visiting schools and societies with his range of interesting and informative talks, as well as keeping busy with his teaching duties. He's also a STEM ambassador as well. And if that doesn't keep him busy enough, he also runs 2 websites. The Astronomical Unit has a wealth of detail on amateur astronomy, from mathematics to choosing equipment to cosmology. And there's also a great section on pseudo astronomy, or as Steve puts it in one of the articles, Astro Crud. Steve does do a talk on this, and I think that could be a very entertaining one for some time in the future. The second website, the Binocular Sky, as his name suggests, is dedicated to astronomy using binoculars. And again, there's a wealth of information to be found there. There's also a free newsletter that Steve publishes monthly, I think it is. Steve, is that right?
Yeah, that's right, yeah.
Yeah. And there's lots of information about what to observe during the course of the year with binoculars and small telescopes. So again, hop over to the website and you can sign up there. Steve has authored numerous articles and 2 books on observing with binoculars. Binocular Astronomy is now into its 2nd edition, and his latest one, Discover the Night Sky Through Binoculars, is available from First Light Optics. We'll post up the links to Steve's websites and the books on the forum as we would do normally, so you can look out for those afterwards. So, without any further ado, with an interesting talk on 10 ways the universe will try and kill you, please welcome Steve Tonkin.
Oh, thank you very much, Raz. Let's see if I can get this. Things always go where you don't want them to, don't they? Green 2, sound on. Yep, share. Great. You should be seeing a title page for this. Well, reason I like this talk, this must be, I don't know how many times I've done it now, but one of the things that I noticed very early on when I started looking at things about life and death and all the rest of it, is that as far as we know, the universe has invented exactly one way that life can exist. I know we're extrapolated from a sample size of 1, which is dangerous and all the rest of it, but that's pretty meaningful. But when we've got literally tens of thousands of ways it's invented to take us out, so in any normal terms, the universe is a complete and utter, sorry, youngster listening, as Shakespeare would put it, a vile, misbegotten wretch or something like that. So anyway, I'm going to look at some of these today. Hopefully we'll just cover a little bit of astronomy, cosmology on the way. Probably a lot of you already know, but we'll try and make it a bit fun. It does get a little bit listy, I'm afraid. Well, 10 ways, so it's going to get listy. And we'll just see where it takes us. We'll just spend a little bit more time on one particular thing than some of the others, which we'll see when we get there. I'm not covering things like space weather, because that's really a talk in itself. So let's crack on. So the first thing we got, hello, thank you, gamma ray bursts. And we'll just take the same sort of series of questions throughout these. So what are gamma ray bursts? Well, they are the consequence usually of either a supermassive star, probably a Wolf-Rayet star, collapsing to form a black hole, or as we now know from some of the Virgo-LIGO stuff, a couple of neutron stars combining. And the important thing about this is, in a few seconds, they release more energy than the sun will in its entire approximately 10 billion year lifetime. So that's a pretty hefty amount of energy coming out, and obviously you don't want to be anywhere near it. And what you get is you get focused gamma ray beams in opposite directions. Excuse me. The beam angle is typically round about 5 degrees. So unless you're in the beam, you're effectively okay. But it has been suggested by some people that it could be gamma ray bursts that have been responsible for the Fermi paradox. That's the thing that Frank Drake suggested there were, I think it was up to 50,000 communicating civilizations in our galaxy. Well, why haven't we found any? Maybe they eventually get taken out by gamma ray bursts before they manage to contact anyone else. So, carrying on with the scheme, how will they get us? Well, if one happened in our galaxy, it would destroy the ozone layer.
Sorry, Steve. Can I just butt in a second? People are complaining about some muffled sound. I don't know if you can adjust at all a little bit, or change your microphone.
No, sorry, I don't know where that's coming from.
I was just saying, I found just turning the volume up, it was fine. It's fine for me here, so I don't know if it's just a local issue with certain people. Sorry to interrupt.
No, that's okay. People need to be able to hear. I'll just check my volumes up as well. Done. No, mine appears to, mine is switched up full now, so I'm afraid
Okay.
there's nothing more I can do about that. Sorry about that. So I'll try to speak more directly at the microphone. So.
Okay, you sound okay to me, so hopefully that's a little bit better. I think we'll just have to crack on, and then if anybody can't hear it properly, hopefully in the recording it will improve.
Yeah.
Okay.
Okay, so if one happened in our galaxy and it happened to be pointing our way, it would destroy the ozone layer completely and bombard one side of the Earth, only one side of the Earth, with lethal radiation. So if you're on that side of the Earth, you've had it. And the consequences of that, even if you're not in the way, they are going to be mass extinction, food chain disruption, and ultimately starvation. So you're really either wiped out by the thing when it happens on one side of the Earth, or you starve to death if you're on the other side of the Earth. A bit like really what happened to the dinosaurs mostly. Apparently most of the big non-avian dinosaurs starved. That's how it was. But it's only a problem if you're in the beam. And this is where we need to start thinking about a whole sort of scale of things in the solar system and the universe. If we took, to try and picture what's going on, if we take something like the sun being the size of one of those about 16-inch paper lantern lampshades that used to be all the craze, then on that scale, the Earth is going to be a 4-millimeter pinhead, nearly 50 meters away. On the same scale, the nearest star is going to be in Brazil. So we're talking about a heck of a lot of space. There's a heck of a lot of stuff to miss, and we're talking about a narrow beam angle. So it's only really a problem if you're in the way. But that, of course, doesn't help if there's loads of them, because statistically you're going to get there. So we need to know how frequent these things are. Long ones, we expect to get one every 100,000 to a million years in the galaxy the size of ours. We detect at least one per day from the universe. And short ones, well, the short answer is nobody knows. They are, obviously, people are trying to find out more about these things. And when gamma ray bursts are detected, the orbiting detectors immediately tell telescopes at the surface, stop what you're doing, look there, to see if we can find out what it is that's causing it. Excuse me. But at the moment, again, nobody really knows how frequent these are. So have they hit us before? Possibly. You probably know there's been a load of major extinctions since the Cambrian explosion. And one of them, the Ordovician-Silurian extinction, which was 445 million years ago, it's one that took out the trilobites and things like that. One of the suggestions for that, mainly because can't find anything else that might have done it, is that we're hit by gamma rays, but we don't know, but it's a possibility that things are there. So what can we do about these things? And this is where a theme will start emerging, I think. And the answer is absolutely nothing, because we won't know about them until they hit. And because information can't travel the speed of light, gamma rays travel at the speed of light. So that's it. Nothing you can do to protect yourself against them. So what's the risk? And the answer to that is it's probably infinitesimally tiny. Say if we have been hit before, it was at least 445 million years ago. So so we can wipe those out and hope that we're lucky there. So let's move on to something that's slightly nastier if they're nearby, and that is a magnetar. Magnetars are slowly rotating, well, we say rotation period about a second to 10 seconds, neutron stars. I think of them as, think of town on the Isle of Wight, probably about the size of Ryde, but more mass than the sun. And They get like starquakes on their surface, it seems. And as they decay, you get these magnetic fields which then decay with it, and they emit X-rays and gamma rays. And they're sort of like an omnidirectional gamma ray burst with a massive electromagnetic pulse on top of it. So you've got something's a bit nastier now. Now somebody's sort of like taking a cruise missile to a boxing match. It's sort of completely over the top. Just while we're on what they emit, it's also now thought that they're probably responsible for FRB's fast radio bursts. But again, that's not absolutely certain, but it's looking extremely likely. So how will they get us? I'll mention there's 30 million of these in the Milky Way, by the way. Yeah, how will they get us? Well, they'll bathe us in gamma rays, could certainly lead to long-term radiation sickness. The electromagnetic pulse could knock out communication satellites. If that happened to a large enough extent, you get global economic collapse. It would make the coronavirus economy shrinkage look minor, really would. And that, of course, would then lead to chaos, as happened. So how frequent are these things? Well, the first one was discovered in 1979. It affected some satellites. And we've been hit at least twice more. In 1998, near Shoemaker had to shut down. That was the one that was going to Eros, I think. And that was a gamma ray burst that was 20,000 light years away. And then in 2004, one affected the ionosphere, and that was 50,000 light years away. And the nearest known one is only 9,000 light years away. So working on an approximate, approximately the same size, and we've got inverse square law. Nearest one, if it decided to be nasty, would hit us with 4 times approximately the energy of the one that caused near Shoemaker to shut down. So what can we do about them? And the answer again is nothing, because we won't know until they hit. And what's the risk? Well, the Armageddon risk is actually quite small, but the risk of satellite disruption is absolutely enormous. And people are really starting to take this side of things much more seriously now. It really happened. There was a coronal mass ejection from the sun, obviously, that took place during London 2012. Fortunately, it wasn't coming this way, but if it had, it would almost certainly have taken out a large proportion of communication satellites. And if it had done that, London 2012 couldn't have happened. And all of a sudden, Parliament, government sort of sits up and takes notice, and they now have a committee working on this at a lot higher degree than they were. But as I said, there's tiny Armageddon risk. So let's move on, because that's probably not going to get us either. Cosmic rays. These are high energy particles that come from hypernovae or kilonovae, sometimes people are calling them now, which are the supernova of massive stars, really massive stars. And they can have energies tens of millions of times higher than the sort of feeble stuff we produce in something like the Large Hadron Collider. So they're pretty powerful. They cause secondary radiation when they enter the atmosphere, and that's what that image in the beginning here is. You've got your cosmic ray coming in, hitting the atmosphere, and then you get this cascade effect. So you get this shower of particles. The secondary radiation forms an approximate ellipse on the surface of the Earth. And so how will they get us? Well, ultimately, they will could cause DNA deletions, and that means you get instability in the genome. Not necessarily a bad thing. If genomes were completely stable, we'd still be bacteria, so just as well. But you are going to get a lot of essentially cancers and possibly teratogenesis on the way. So it's not a brilliant thing, and they also cause errors in computer chips. You get a flip bit, a 0 to a 1 or a 1 to 0. Average is apparently 1 error per 256 megabytes of RAM per month at Earth's surface. The higher up you are, in other words, the less protective atmosphere you've got, the more this becomes a problem. And in things like the space station, I believe they have to reboot laptops and such like fairly frequently, and it's not Windows 10 playing up again, wanting to reboot for you. Okay. So how frequent are they? Well, they're constant, and you can't escape them because they even get to you underground. So what can you do about them? Well, even though they do penetrate the ground, living at low altitude is a good idea because the effect is much lower at low altitude. The effect at high altitude is a lot higher. And the risk, well, the people who are most at risk are aircrew and astronauts. You've got here safe limit 1 millisievert per year. Don't worry too much about what a sievert is. It's a measure of radiation that takes into account the intensity of the radiation and its ionizing potential. It's equivalent to 7 16-hour flights at cruising height of a jumbo. Aircrew, you see here, they typically receive more than 3 times as much as the safe limit. And this is why there is a statistically higher chance of aircrew getting cancers and such like. So let's move on, because we can't do anything about that. Hypervelocity stars. If you remember some of your history of astronomy, when people started looking in detail at globular clusters, which formed at the same time as our galaxy, as far as we know, they discovered in there some hot blue stars. Hot blue stars are new stars. If the globular cluster is old, it should be red stars, old stars. So they called them blue stragglers initially because they thought, well, something, you know, it's a delayed evolution or something like that. But eventually what became clear is that what you're getting in that real dense star environment, you get collisions and interactions, and that ultimately kicks off another round of nuclear reactions, and the stars, you know, what was 2 stars kicks off again as 1 star. And this is what's involved in this. So the idea is you have a star system which moves near the black hole in a galaxy. 1 star falls in, and you get a binary pair that's ejected. The binary pair leaves the galaxy and ultimately merge to form a blue straggler. And the blue straggler itself is what travels away from the galaxy. So you get one of these things. It's a huge star. It's traveling at around about 1.6 million kilometers an hour. Now, all of a sudden, Earth's target area has increased enormously. We are no longer just this pinpoint, this pinhead, left just under 50 meters from our hypothetical lampshade-sized sun. That has suddenly increased to a diameter of about 5,000 kilometers, because what it would do is get us with this gravitational disruption. It only has to come near in order to start causing collisions and disruption in the Oort cloud, and that ultimately could send stuff down on us. We wouldn't know about it. You know, one could have come past and already done this. You won't know about it for up to tens of thousands of years afterwards. That's how long it takes stuff to get from the outer Oort cloud to us. So, yeah, it could already have happened, of course. But if that happens, then, or if one came very close, you could certainly get cataclysmic collisions within the solar system. So that could be an interesting possibility. So again, how frequent are they? Well, we know 34 of them. There's another 5 possible so far. That might have gone up since I last looked at these data. Fortunately, none of them is coming this way, and the nearest one is 70 light years away, so we get approximately 675 years warning per light year. So we should be reasonably safe, and if one does come, eventually those people with "the end is nigh" placards would eventually be right, but not in their lifetime. Satisfaction from that. So what can we do about them? And of course, the answer again is nothing, but they will be detectable for a few millennia beforehand. So we can have, to just spend a long, long time with the human race worrying about what it's going to do. The risk, well, actually, even though we are this now changed from this sort of 50-meter radius target to this 2,500 kilometer radius target, 5,000 kilometer diameter target, we are still a pretty tiny target in the whole scheme of things. When you consider the size of the entire Milky Way. So again, the risk is very, very minimal. So let's say minuscule. Let's not worry about that one and move on to the thing that Leo was asking me about in the waiting room earlier, while people were waiting. Rogue black holes. So this one's for you, Leo. What are they? Well, they're the result of a gravitational wave kick from a black hole merger, and they travel through intergalactic space at several million kilometers an hour. And of course, because they've consumed all of the gas and dust and debris around them, they're invisible. So we don't get an event horizon or anything we can see around there. So the only way we can see them is by their effect on the light of things that come from behind them. How would they get us? It's back to the same way as the hypervelocity stars would. Massive gravitational disruption. If one came nearby, Earth would be ripped apart, be spaghettified. If you don't know about spaghettification, imagine you're going into a black hole feet first, and the gravitational gradient is so great that your feet would accelerate in faster than your head, so you'd be stretched out, spaghettified. So that's spaghettification. And then we'd be added to the black hole singularity, and what happens there, we don't know, because the laws of physics break down. That's if it came close to the solar, it came close to Earth. It would have to come pretty close. I mean, it's not as though, if something passes us at, say, Saturn's distance, but it's going to have that much effect, because it doesn't suddenly have any more mass, just an enormous gravitational gradient. If it only came close, then we're back to this disrupting the Oort cloud, debris, and the rest of it coming in down Earth. So we could have another, an even later heavy bombardment, the thing that seeded Earth's crust with all the stuff that had originally sunk to the middle, about 3.9 billion years ago. How frequent are they? Well, the real answer is this: nobody knows. What can we do about them? Well, you already know the answer to this one, so there should be a chorus of nothing. And what's the risk? It's actually been estimated, and that is great. It's tiny. There are 16 zeros there, and I thought just nicer to write it in that way, so you can see the length of the number. You can see that actually this is a tiny, tiny, tiny probability, but it exists. Probabilities that are tiny still happen. Evolutionary changes that got from archaea to us, excuse me, all have tiny probabilities, all mounting up. But here we are. So, let's not be too complacent and go on to rogue planets. Rogue planets, well, pretty obvious, really. We've done rogue black holes and rogue stars, hypervelocity stars. What are they? They are planet-sized bodies, obviously. They're either ejected from their star system. Now, at the beginning of the solar system, there were many more planets, almost certainly. And in the chaos that was going on there, some would have been thrown into the sun and some were thrown out. And eventually it settled down to what appears to be a fairly unusual configuration, which is the one we have now. If you look at other known star systems, none of them look very much like our solar system. But anyway, that's by the by. But it's also possible that planets can form in interstellar space. So they may never have been gravitationally bound to any star at all. And that's interesting. So it means we might be quite an uncertainty of how many of these there can be. But the thing is, they do is they orbit the galaxy directly. So how will they get us? Again, collision directly with the Earth or disruption of the Oort cloud. So again, we're coming down. We don't know what that is, but how frequent are they? And the answer is nobody has a clue. It's a low estimate, but there's one of them for every 2 stars in the Milky Way. In fact, that one's just gone down slightly recently, but not significantly. It's still that sort of order of magnitude. But the high estimate is 100,000 rogue planets for every star in the Milky Way, which is planets unconnected to a star system. So that's a pretty massive number. The nearest one detected is this beast. I won't read it out, you can read it for yourself. And the discovery of this was announced in September 2012. Those of us who were alert in around that time to what was going on, what the conspiraloons were on about, might remember what was meant to happen in December 2012, the Great Mayan Apocalypse. And part of this was going to be attributed to a planet X, which various people say, you know, it was predicted in ancient Babylonian texts, it's been predicted, and this has been predicted, and that, of course, it hasn't been. But it's, this is what they came up with. And when this was announced, all of a sudden, internet conspiracy lunacy goes wild. You see, yes, we were right. We told you it was coming in. Here it is. Because, yes, this one is coming our way. Hang on, folks. It's 130 light years away. How fast does it have to be traveling to get here in 3 months? We'll say, never, ever let a complete ignorance of cosmology, physics, mathematics get in the way of a pretty rubbish conspiracy theory. So let's move on, because we know about these now. So what can we do about them? And again, the answer is nothing. Risk. Well, it's not going to keep me awake at night, let's put it that way. Let's move on to something slightly more controversial. Verneshots. If you've read Jules Verne's book, was it From the Earth to the Moon, you know how they got people there. Socking great cannon. Of course, couldn't work in real life because the acceleration to escape velocity would probably kill you, but never mind. So what are they? Well, the older parts of Earth's crust, which are really, really thick, are called cratons. And you've probably heard that there's some thought about there being a hypervolcano, a supervolcano, underneath Yellowstone National Park. I think it gives rise to that, and concerned that if that goes, it could take out most of the United States, or most of the North American continent, cover it in ash and all the rest of it, make it uninhabitable. That's got nothing on a Verneschot. So what it is, you've got this idea that you've massive buildup of carbon dioxide underneath the craton, and it could be forceful enough to launch a huge amount of crust and mantle into a suborbital trajectory, which is nasty enough. But then something else happens. It's left this socking great void in Earth's crust and in a bit of the mantle as well. So this huge pipe through which all this stuff has come collapses very, very rapidly. And you get a hypersonic shockwave that hits the remainder of the craton, pulverizes it with an explosion equivalent to approximately 120 gigatons of TNT, is what the theorists on this say. That's 6 million times the power of the Hiroshima bomb. So you get 20 gigatons of debris blasted into the atmosphere. Lava fills the hole left behind. And then the impactor, the thing that went to the suborbital trajectory, that comes down somewhere else. How nice. How will it get us? Exactly like an incoming asteroid, but much, much, much less warning. But fortunately, also much lower velocity. So much less damage than you'd get from a similar size asteroid. And the question then becomes again, how frequent are they? Well, they may never have happened, but some geologists have postulated that they happen every 100 million years or so. And again, there has been some suggestion, I'm not sure how seriously it's taken, I don't think very, that one of these could have been responsible for one of the major extinction events. It was even suggested after the Tunguska event that this was such a phenomenon. It wasn't. We now know that absolutely certainly that it wasn't. So what can we do about them? And of course, again, nothing. And this is where, if we're in a room together, I'd be looking for my exits, because risk probably zero, because they probably don't exist. So why have I even been bothering to talk about them? Because I think they're interesting. Moving on. Something that's also interesting because they're pretty. Galactic collisions. So what are they? They are exactly what it says on the tin. Galaxies, two or more, collide and interact. And this happens all the time. We know it does because we've got images of them. You get massive star formation as the interstellar gases combine. But we need to just sort of modify our picture now. I had this thing before where we had, you know, sun-sized stars 5,000 kilometers apart, if they're that big. Take them down to ping pong ball size. And all of a sudden, something we can actually imagine, we take average star size down to ping pong ball size, and the average separation of stars in the spiral arms of our galaxy would be scaled to just over 500 miles. So there's a heck of a lot of space. And even in the galactic core, where they're really densely packed, or so we like to think, we're talking about ping pong balls every 2 or 3 miles. So there's a heck of a lot of space. So unless there's this direct interaction between another star and our solar system, we may escape completely unscathed. This said here, that's the scale star density. If we do get there, if we do get a direct interaction, again, we're back to the gravitational disruption that we keep coming on. So it looks like, you know, most of these things that might get us, ones I've chosen anyway, because they're ones we see around us, it would ultimately be gravitational disruption doing for us. They're happening around us all the time. You already know the answer to this one. Nothing can do anything about this. What's the risk? Things have changed. The risk is certainty. It is going to happen. We and the Andromeda Galaxy will, depending on who you listen to, but approximately 4.5 billion years' time, we will merge. And we will merge to form an elliptical galaxy. I've got a little video which I'm going to show you on this because I think it's pretty. I'm afraid the intro is slightly long, but it gives you time to read it. If I can get it. There we go. Scale bottom right. And you can find animations like that on the internet. So that's it's quite a beautiful dance of the galaxies there, if that animation is correct. Let's move on. I'm sure some of you are familiar with Arthur C. Clarke's book, Rendezvous with Rama. And I'd like to read the opening passages from that because it really puts things into some sort of perspective. So it is Rendezvous with Rama. Sooner or later, it was bound to happen. On June the 30th, 1908, Moscow escaped destruction by 3 hours and 4,000 kilometers, a margin invisibly small by the standards of the universe. On February the 12th, 1947, another Russian city had a still narrower escape when the second-rate meteorite of the 20th century detonated less than 400 kilometers from Vladivostok with an explosion rivaling that of the newly invented uranium bomb. That was a Sikoti-Allen event. And I think actually First Light Optics can sell you fragments of that. Iron meteorite, a fragment. Okay. In those days, there was nothing that men could do to protect themselves against the last random shots and the cosmic bombardment that had once scarred the face of the moon. The meteorites of 1908 and 1947 had struck uninhabited wilderness, but by the end of the 21st century, there was no region left on Earth that could be safely used for celestial target practice. The human race had spread from pole to pole, and so, inevitably. At 0946 GMT on the morning of September the 11th, in the exceptionally beautiful summer of the year 2077, most of the inhabitants of Europe saw a dazzling fireball appear in the eastern sky. Within seconds, it was brighter than the sun, and as it moved across the heavens, at first in utter silence, it left behind it a churning column of dust and smoke. Somewhere above Austria, it began to disintegrate, producing a series of concussions so violent that more than 1 million people had their hearing permanently damaged. They were the lucky ones. Moving at 50 kilometers a second, 1,000 tons of rock and metal impacted on the plains of northern Italy, destroying in a few flaming moments the labor of centuries. The cities of Padua and Verona were wiped from the face of the earth, and the last glories of Venice sank forever beneath the sea as the waters of the Adriatic came thundering landward after the hammer blow from space. 600,000 people died, and the total damage was more than $1 trillion. But the loss to art, to history, to science, to the whole human race for the rest of time was beyond all computation. It was as if a great war had been fought and lost in a single morning, and few could draw much pleasure from the fact that, as the dust of destruction slowly settled, for months the whole world witnessed the most splendid dawns and sunsets since Krakatoa. After the initial shock, mankind reacted with a determination and a unity that no earlier age could have shown. Such a disaster, it was realized, might not occur again for 1,000 years, but it might occur tomorrow. And the next time, the consequences could be even worse. Very well. There would be no next time. 100 years earlier, a much poorer world with far feebler resources excuse me, had squandered its wealth attempting to destroy weapons launched suicidally by mankind against itself. The effort had never been successful, but the skills acquired then had not been forgotten. Now they could be used for a far nobler purpose and on an infinitely vaster stage. No meteorite large enough to cause catastrophe would ever again be allowed to breach the defenses of Earth. So began Project Space Guard. And I'm going to come back to Space Guard because it comes back again. And this wasn't the first thing to predict something like this. H.G. Wells in 1897 wrote a short story called The Star, which again is about asteroid impact. These things have been worried, people have been aware that these things are possible, likely even, for a very long time. And it's only relatively recently we've actually started to think about doing anything about it. So back to our, what are they? Well, they're lumps of rock, anything from 1 meter to about 500 kilometers diameter. That's your approximate definition of an asteroid. Let's have a look at this. The dots will not be to size, scale, but just to give you an idea. In a solar system in 1800, EP4 series was discovered, this is what we had: Sun, Mercury, Venus, Earth, Mars, and of course Earth and Mars is new. And that was it. When you get on to 1900, 100 years later, the green dots represent meteors, or asteroids, sorry, and the red dot is one that crosses Earth's orbit. So red dots are Earth orbit crossers. By the time we get to 1950, we have something that looks like this. By the time we get to 1990, we have something that looks like this, and yeah, it's quite a lot of red now. By the time we get to 1999, it looks like this, and there's no point going any further till it would just be a sea of green and red. So that's a sort of idea of the scale of the problem. How will they get us? Well, it's two ways. Either impact, it should be functioning. Okay. Try again. Okay. So it blasts, melts, throws stuff into the air, and then you get the beginning of an isostatic uplift. Why most craters on the moon have the hills in the middle, and that's there. Or you can get the airburst, which is this. Apologies for, I think that's in Italian, but it's the best GIF animation I could find. So you have a meteoroid coming in, it turns into a bolide, fireball. As it gets down close to the stratosphere, it starts disintegrating, and eventually you get bits that come down and hit the Earth. So how frequent are they? Well, we know about the Tunguska event. That was 1908, June 17th. It was probably a comet nucleus, actually. 100 meters across, 100,000 tons, last equivalent to 15 megatons of TNT. Compare Hiroshima, 20 kilotons. There are eyewitness accounts of this that you can read. I won't do it now, it's go on forever, but people being thrown into trees, people having limbs broken. Fortunately, it was a relatively uninhabited place with herders, so not a lot of people were killed. When it eventually sent an expedition there to have a look at it, top one's an artist's impression, obviously, by the way, this is what they photographed. And what you have here is you have trees away from the epicenter of the explosion, are flattened away from it. But the ones underneath it are still standing, and they've just had their branches stripped off. How you can be pretty certain it's an airburst. So the force came down and stripped the branches off the trees, and that's what they found. Where did the thing land? Don't know. There has been some suggestion that a lake might have been the impact crater. Again, nobody's really sure. But we've had something much more recent. We were all getting excited because the night after the morning this happened, some of us were out trying to find holes in the cloud to see this asteroid that was going to pass within the circle of Earth's geostationary satellites. And if anyone remembers that, we completely failed. There were some clear patches in the sky, and none of them ever occurred where the asteroid was. And this was Chelyabinsk. So February the 15th, a little bit over 7 years ago, it was something the size of a building, only 17 meters, about 11,000 tons, still 25 times the power of the Hiroshima blast. Now, what happens there was a lot of people in Russia at the time had dash cams, because there's a lot of insurance scamming going on with accidents that weren't accidents. So this was one way of protecting yourself against this sort of thing. But what it did mean is there's a heck of a lot of footage of this stuff. Turn your volume up. It's much better with the volume right up. beneath it at all. This was miles away. Nobody was killed. About 1,500 people were hospitalized, almost all of them due to laceration from flying glass, because saw a bright light in the sky, went to the window to have a look at what was that, and then of course, in the shockwave hits later. My favorite story from that is a primary school teacher saw the light in the sky and just thought, time for nuclear drill, and got all the kids to hide under their desks, which is what they were meant to do in that case. Every single window in the classroom was shattered. There was glass flying all over the place. Not one child was injured. The teacher herself had a lacerated arm, but that was it. So, you know, these things happen. And okay, that we know about because it landed or it exploded quite close to somewhere populated. It's significant evidence that these things are actually quite frequent. And they normally land either in the sea, which is where you'd expect most of them to land, because 2/3 of Earth's surface is sea, or in deserts. And apparently, one a few years ago hit the Sahara, and we might be getting bits of it when another NWA fragment set hits the market. I don't know for sure about that. It's not a great one of my interests. Okay, so let's try and put these sort of things. Let's put Tunguska into the sort of context of something we might recognize. If Tunguska was London, the black is the blast area, the bit that was absolutely flattened. The blue is the M25, so it's land right over the middle of London. Just about everything inside the M25 will be flattened. So that's the sort of thing we're talking about there. Okay, that's 10 million people there. So the answer is, well, the question is, what can we do about them? And there are things we can do. This is the thing. We now have options. We can evacuate. But can you imagine trying to evacuate 10 million people, and where the heck you're going to evacuate them to? I mean, it'd be absolute chaos. Destroy, the Bruce Willis Armageddon option. Probably the most stupid thing you can do, because what we've got here is we have a single predictable impactor. You destroy it, you turn it into a cluster bomb, which becomes less predictable and won't do a heck of a lot less damage. Or you can deflect it, and that's where the smart money goes to. I'm going to show you some stuff now, and this comes from SpaceGuard UK. Jay Tate, who incidentally was a great person to give one of these talks, actually. He's brilliant on this. Director of SpaceGuard UK, and he's using this stuff with his blessing. Okay, what we're going to look at is how people like local governments and governments work out how much money is worth putting into doing something. Okay, so what you have is you have a chart which lists number of deaths at the top. That's a logarithmic scale, obviously, and the interval between events. And you have various bits on this. So you have something around here is tolerable. You're not going to spend a heck of a lot of money trying to mitigate against something that is only going to kill 10 people in 1 million years. Yeah, that's really daft. You get what's called a local scrutiny line, which is this is where we need to start looking at it, and then you get the intolerable region. So you start putting things into there, but what we try to do is to try and get risks to as low as reasonably possible. And let's take something like the Chernobyl reactor. When that went up in 1986, I'll know that its place on this chart would have been about there. Definitely the intolerable. $1.8 billion, or pounds, sorry, no pounds, has been spent bringing it down to here, to where it is now. So that type of, that Soviet RBMK reactor is now, we are told, a heck of a lot safer and no longer in the intolerable. Aircraft crash comes in about here. And major aircraft crashes don't happen that often. When they do, they take out possibly a few hundred people. So that's there. And we think they are intolerable. We work against them. So that's something very close to our intolerable line. Tunguska on a major city, if it hit, would be here. Again, in the terms of global thing, it's actually not that, yes, it would take out a lot of people, but you don't expect it so often. And it's not that great a killer. But you take a 1 kilometer impactor and you're getting nowhere near the size of the thing that took out the dinosaurs yet. We're already in the intolerable. And if you take in the tsunami threat, we're round about there. So this is the sort of things we're looking at. So let's take something like a 1 kilometer impactor and do some economics. So our 1 kilometer impactor, we'd expect them about every 100,000 years. We've expected to take out about 25% of the population. That means UK casualties would be about 15 million. Now, you may not know this, but your life has a value, every single one of you. It depends on where you are in your economic productivity, but the EU puts a value purely on your life. And it's somewhere between £825,000 and £3.1 million. So this is somebody who's in their prime economic activity. This is someone like me who's supposedly long past retired and all the rest of it. Okay. So if we take an average, sort of, down the middle there, let's say 1.5 million because it makes the sums easy, then the total cost in the actuarial value of human life is 22,500 billion quid. Doesn't that make Rishi Sunak's thing for helping the businesses look insignificant? And yes, and Sunak's thing is not insignificant. This is even less insignificant. And that means if you divide that by that, that the cost per year is 225 million. So ultimately, if we are spending less than this, the chances are we're winning. We're getting better value for money. We're spending this on asteroid mitigation. But this figure here doesn't include things like cost of property, commercial losses, heritage. It's just the, I say just, you know, it is the actuarial cost of human life. Where does we fit in with this? Well, the entire UK Space Agency expenditure, last one I can get hold of, is 375 million. We don't actually do asteroid mitigation directly. We do it through the ESA. Our donation to that is of the equivalent of a few £1,000. So, but this is politics. This is people who are able to look at the next 3 years, not look at the big picture of things we need to be actually doing for the service of the human race, in my opinion. Okay, so one of the things that ESA and NASA are doing in a couple of years' time, they're launching something called AIDA. I'm not going to play the video. It's work plan doesn't work brilliantly over Zoom. And that is to try to deflect an asteroid. It's actually a binary asteroid. They're going to try and deflect one of the members of it by stashing a spacecraft into it. Never been done before, although we do know how to deliver a spacecraft to an asteroid, and it's going to be watched and see if that's possible. But the Space Guard idea, remember the bit from Arthur C. Clarke, was that using what we already have. And this is where I think the smart is. So the idea is we use a weapon that was, it was called at the time, this is the time of Reagan and Thatcher and that, someone called it the ultimate capitalist weapon, because the idea is that it kills people but leaves property intact. Well, it doesn't. It's the enhanced radiation device or neutron bomb. The idea was it would paralyze Eastern Bloc tank crews if they came cruising over Western Europe. So what you have here is you have a spacecraft which has 2 bombs on it. The first one is a small one, and the idea is to excavate a crater, because that means the second one, which is the enhanced radiation device, neutron bomb, the pure radiation pressure from that can be effectively focused by the crater, so it can really shift out the way, and you don't have to shift it very far. If you remember the Apollo 13, you know, for the capsule on re-entry to skip off Earth's atmosphere, it only had to be a tiny angle out. You only have to change the path of this a tiny amount. You're not, certainly not trying to destroy it. And that is where I think the smart money is at the moment, on how, if something happened tomorrow, this is about all we could do. There have been other things you've probably heard of that people have put into place, you know, things like painting one side of the asteroid white, so it changes the way it interacts with solar radiation to push out the way. But yeah, that's really going to happen. Or laser bees, get little spacecraft with lasers and sort of blast one side of it with lasers to try and deflect it. Well, we don't have them. What was the other one? Yes, park a massive spacecraft next to it and hope the gravitational interaction will pull it out the way and deflect enough. Possibly, but this is actually got. It's not joined up, and people like Jay Tate, who's actually ex-military, you know, realize that this is where we can do it. We have everything we need. We just have to put it together, and as Arthur C. Clarke says, you know, put it to a more honourable purpose. Okay, so let's stop being serious and doom-laden and all the rest of it, and me having my normal go at politicos. So we might survive all those 9 ways that the universe has tried to get rid of us. But it's still got one nasty little trick up its sleeve, and it's this: solar expansion. So this, or this, is the size of the sun as it is now to scale. This, or this, is the size of the sun when it becomes a red giant. And note the diameter, 2 astronomical units. It means, of course, radius, 1 astronomical unit. What's the distance from the Earth to the sun? By definition, 1 astronomical unit. So how does this happen? As I'm sure most people know, the sun is this huge nuclear furnace. So you've got a nuclear reaction going on in the middle, and that's pushing outwards, and you've got gravity pushing against it, pulling inwards. So what you've got is you've got this dynamic balance going on. Gravity in, nuclear pressure out. And it's held that for probably the last 4,500 million years. So it's pretty stable, even though it's losing hundreds of tons of mass every second. It's big. Ultimately, this nuclear reaction is going to stop. When that reaction stops, gravity starts to win. As gravity starts to win, we are compressing effectively a gas or plasma. That will heat it, and nuclear reactions will kick off again, but not just in the core now, but throughout the body of the star, our sun, and that means it will expand. As it expands, it cools and goes red, and hence we have a red giant. And most people think that the sun's going to get us, I think it's about 5.4 billion years before it becomes a red giant, and that's when it's going to get us. That is wrong. Because as the sun enters its red giant phase, it's going to lose mass, enormous amounts of mass. That means Earth's orbital radius is going to increase. So we will almost certainly escape being engulfed by the sun. Isn't that nice? Are we safe? No. If you think that, you haven't been paying attention. Because the universe is out to get us, and it will. After about 3.5 billion years before the sun enters its red giant phase, it's going to double in size over about 500 million years. It'll become a subgiant. Its luminosity will double. Earth will become hotter than Venus is today. So the surface becomes hot enough to melt lead. The oceans disappear. Oxygen in the atmosphere reaches escape velocity. And what can we do about it? Nothing. Risk, absolute certainty. We've got about 2 billion years left if we manage to last that long without doing something stupid to each other along the way. And when you consider that we've only been around as Homo sapiens for about 200,000 years, well, What this tells me is that actually, while we're here, let's try and make it nice for us, for ourselves and for each other, because this is, you know, we're not going to be forever, so we might as well enjoy what we've got. So that's just about it. So the final score is humanity 9, if we survive them all, universe 1. That's pretty good, huh? But we still lose because, as I told you right at the beginning, the universe is a vile, misbegotten wretch. So that's just about it. Daz mentioned at the beginning, website, social media and that. I've got 2 websites, he said, Astronomical Unit and Binocular Sky. This one's my general talks, astronomy tutorials, as you mentioned, pseudo-astronomy, Astro Crud, on web, Twitter, and Facebook. Binocular Sky, similar astronomy binoculars, monthly newsletter. My idea is that this will always be free, and we keep doing that until I'm still on the green side of the turf. And the books that Daz mentioned are these 2, both available actually or available from the website. Thank you for listening, and thank you for putting up with the little commercial plug at the end. Thank you.
Thanks, Steve. Thanks very much indeed. Right up until the last minute, I thought we were going to escape from all of that. I thought I could sleep soundly in my bed, but no, it's going to get us. It's going to get us in the end. Okay, so hopefully people are going to send some questions. And there's a couple of observations also have come in. So I got these right. Ian thinks that Concorde actually had a gamma ray detector on board the plane. Steve, I don't know if you know about that.
I don't know about that, and I should do, because one of the things I did when I was at university was a project on the environmental impact of Concorde. And I know absolutely nothing about that. So sorry.
No, that's fine. That's fine. Happy Cat, hi, Happy Cat, one of our regulars, always asks lots of questions. So just a thought, could the pumping of gas, and I guess he's referring to things like fracking and all the rest of it, could those sorts of activities lead to Verneshots, do you think?
Most certainly not. I'm not convinced about Verneshots. You know, I think they're fantastically interesting idea, but I think the evidence is out, or the jury is out, shall I say, on whether or not there's sufficient evidence that they've actually happened. But no, it's because things like fracking don't cause a build-up of pressure underneath. They will actually reduce pressure. So you're more likely, I would imagine, to get some sort of substance, but you shouldn't, because they put gas grit into the fractures anyway to hold them open. So that shouldn't happen. Right.
Okay. Understood. Michael Wilkerson. Evening, Michael. Hope you well. Actually thinks that we might merge with the large and small Magellanic clouds before Andromeda. I have to say I'm not. I don't know. That's
no. I don't know either, but thanks, Michael. I'll see if I can find out something about
that. And then another observation from Steve Richards. Evening, Steve. I've seen your on screen somewhere about. He is reliably informed that some image sensors are actually transported on a specific arcuate route to avoid the cosmic rays.
I believe they are. Yeah, it's but one of the things that cosmic rays are meant to have done. I think I may have the details a little bit fuzzy here. Qantas flight, the avionics, they told the flight crew that they were in a 50-degree climb all of a sudden. So they did what they thought they should do, which is drop the angle by 50 degrees, and we actually went into a 50-degree dive. Various passengers had to be, well, bounced off the ceiling. Several people hospitalized as a result of that. And that one of the suspicions of that is cosmic rays hitting the avionics stuff and just completely fouling up the flight control. So,
Okay.
you know, these things aren't benign, if that one is true.
Just Habitat was referring to the carbon storing more than the fracking. So, you know, there's talk of storing carbon under the ground.
Okay, sorry, my bad.
Habitat also asked, which of these phenomena was likely to be the one that took out radio signals around 6 years ago?
I don't know.
I wonder if you're talking about the Canada one, which was that?
Oh, that was the 1970s, 80s, wasn't it? The one that took out the Quebec, the one that took out the Quebec equivalent of the national grid was a relatively small coronal mass ejection, and the big coronal mass ejection was 1859. It was a Carrington event, when telegraphy was just going, and it induced current into telegraph wires, and their beautiful wooden boxes and that started catching fire, and operators started getting shocks and all the rest of it. And it was Carrington, who just north of where I do, actually, a Hampshire person, I believe. Actually, Matt, he was observing the sun that day, and he saw this bright spot, which is why it's named for him. But yeah, that's a dangerous one, and certainly space weather does have a continuing effect on radio signals, on well, ionosphere levels, and so on. So it's something, but that is a talk in itself. It's actually much more complex than it sounds. Just from, you know, we say, oh, it's just charged particles from the sun, solar wind, and all the rest of it. So yeah, it's not one I do, but I can put you in touch with someone who does if you want.
Okay, yeah, that'd be good. Steve Clifton asks, are the cameras on the Hubble Space Telescope affected in a big way by cosmic rays?
I think they are, because you actually pick up cosmic ray blips on the raw data, don't you? The same as you do with the SOHO stuff and things like that. They're actually quite noisy from cosmic rays. So I think certainly the imagery is, but it's something that obviously, you know, it's noise that you get rid of effectively by stacking, isn't it?
Yeah, yeah. Here's a good one from Simon M. Thanks, Simon. Was the calculation for the asteroid cost, in quotes, based upon one incident? And should you integrate for all impacts and sizes? So the cost essentially becomes so high that in the end, you also end up doing next to nothing.
No, because if we're talking about that, you know, that's the sort of thing we're sort of worried about. Because it's that size event is so infrequent, and bigger events are even less frequent. And apart from that, we think we've got all the big asteroids anyway now. It's certainly nothing that we know about is going to hit us within the next 200 years. I mean, that's pretty certain. And the probability of there being something we don't know about is pretty small, because we're now detecting stuff around about the 100-meter size. You know, it's down to that sort of detection size. I mean, it's not easy. I mean, some of these things are the color of coal. So if they're in the direction of the sun, you've got almost no chance of detecting them. Probably more likely is something like a comet coming this way. But it's, although, you know, people like H.G. Wells have been predicting this stuff since the late 19th century, there's still a heck of a lot we don't know about them. And it's, you know, of course, why scientists do science, isn't it? Because there's so much still to do. People haven't stopped looking and trying to learn about these things.
No, indeed. No, indeed.
Can I ask a question, please?
Yes.
What didn't make the top 10? Was there a sort of almost almost made it list?
Yeah, I was going to put in space one, then I realised it's too big. I was thinking about doing a few things that we do to ourselves as well. But actually, I'm sort of racking my brains now, because I first put this talk together about 10 years ago, and the original notes, I've got them somewhere, but I'm not quite sure what they are. I can't actually, memory's going, I can't remember what I kicked out. I think I got up to about 15 things, and I winnowed it down to 10, but I can't remember what the other 5 were.
Righto. Well, there's lots of thanks coming in, Steve. That people thought it was a really interesting talk. Although Ian says he looks like he's picked the wrong week to quit drinking, but I think he might be okay for a day or two. But
Yeah.
no, that certainly was very much enjoyed by everybody who joined. So unless anybody has any other questions, I think we'll call it there. Steve, thanks very much indeed for your time. It was
to mention
really
next week's speaker. Sorry, just to,
oh yes, please do.
So next week we've got Peter Williamson, who was going to be talking at the Star Party last year that got flooded out. So he's going to do the talk that he was going to be giving us, which is Herschel to Hawkwind.
Oh, I've seen that. It's really good.
Interesting. Yeah.
Yeah,
from Herschel to Hawkwind. So we're looking forward to that. We were looking forward to that last year, so we got there in the end.
Yeah, absolutely. Okay, so and again, obviously, we'll post up. Excuse me. Post up details in advance. Helen's just posted something. Helen's posted a link to the LSST. Is looking for asteroids. So. Click on that, follow that link, and you can read up on some stuff that's going on there. Oh, quick last question. If the moon was hit by something big enough to take out a chunk, would this impact us?
Almost certainly not.
There we go. There you go, Noddy. That's a no then. So again, you're okay to keep drinking and sleep soundly, at least for the next few days. Steve, that's great. Again, thanks very much indeed.
Thank you, Steve.
Yeah.
My pleasure.
Look forward to having you again soon.
Everybody stay safe.
Indeed. Thanks, everyone. We'll see you all again very soon. Thank you very much.
Bye-bye.
Bye.